All right, let's just dive right into this explainer. If you've ever watched a bilingual person seamlessly switch between English and Spanish mid-sentence, you know it's basically a neurological magic trick. It's something that has absolutely puzzled neuroscientists for decades. But today, we're unpacking a groundbreaking study that finally lets us peek under the hood of the human mind to see exactly how we pull this off.
Right, so here is the ultimate bilingual paradox that we're going to unravel. Think about it for a second. You've got thousands of words stored in one language and thousands of perfectly matching words in another. When a bilingual person wants to order a coffee, how on earth does their brain select the exact right word in the exact right language without accidentally grabbing its translation? The mental filing system required to keep all this separate but instantly accessible? It's staggering. And to really appreciate the sheer scale of this cognitive mystery, consider that managing just two languages is child's play for some communities. Take places like Arnhem Land in Northern Australia, for example. Navigating 6 or 7 different languages every single day is just the norm there. This basically proves our brains aren't just capable of holding a spare language in the trunk, they are built with this incredibly robust, scalable architecture for organizing multiple, massive webs of meaning all at once. Okay, moving on to section 1, searching for translation cells. Let's see if we can find specific neurons that basically act as biological dictionaries. Because for the longest time, the most logical theory was just that. We might have dedicated translation cells, a single neuron whose whole job is to connect the English word to the Spanish word. Well, to find out, researchers did something incredible. They literally looked inside the hippocampus of bilingual epilepsy patients. Since these patients already had microelectrodes implanted for medical monitoring, scientists got this incredibly rare window to record single neurons firing in real time while the patients listened to stories and spoke out loud in both languages. Now, you'd probably assume there are dedicated cells firing equally for dog and parrot, right? But the data actually reveals that these cross-language neurons are incredibly rare. Across all the listening and speaking tasks, they found that only about 5.2 to 19.4% of the neurons showed a similar firing pattern for matched words across the two languages. So yeah, these biological dictionary cells do exist, but they are absolutely not common enough to be the main engine driving our ability to understand and translate multiple languages. Which brilliantly illustrates our cognitive mystery. If specific translation cells aren't the secret sauce, how are these languages actually linked up in the brain? If it isn't relying on direct, one-to-one cellular bridges between English and Spanish, well, there's got to be a much more profound underlying structure at play here. And that brings us to the core discovery of this whole research. Section 2, the geometry of meaning. The real answer lies not in a single cell, but in a vast, three-dimensional constellation of meaning. So, here is the crucial takeaway. Words are actually stored as physical distances apart in this sort of neural galaxy. Think of it kind of like a literal map. Dog and cat are clustered super close together in this neural space because, obviously, their meanings are related. But dog and fork, they're miles apart. And what the researchers found is that the brain relies on the exact same set of distances, this shared neural geometry, to understand concepts regardless of which language is being spoken at the time. It's fascinating when you map it out, because the distance between dog, wolf, and fork forms the exact same geometric triangle whether you're thinking in English or Spanish. If you plot out the neural patterns for the Spanish equivalents, so perro, lobo, and tenedor, they form the exact same shape. This map of meaning is completely universal. It is so mathematically consistent that researchers could literally rotate an English cluster of words in the brain and accurately predict what the Spanish neural firing pattern would look like. Crazy, right? But wait. This brings us to the grand twist of the whole investigation. Because if Spanish and English share the exact same conceptual map, and they rely on the exact same group of neurons in the hippocampus to create that map, how does the brain know which language to actually output? Why doesn't a bilingual person just spit out a random mashup of Spanish and English words when they're talking about a dog? Section 3. Same neurons, different angles. Let's look at how the brain uses a genuinely brilliant mathematical trick to keep our languages totally separated. See, instead of using completely different areas of the brain for different languages, we recruit the exact same group of hippocampal neurons. But, and here's the kicker, we view that semantic map from completely different angles. Imagine you're looking at a beautiful 3D sculpture. If you shine a flashlight on it from the left, it casts one specific shadow on the wall. Shine it from the right, and it casts a totally different shadow. It's the exact same sculpture, but a different output. The brain does exactly this with language. It uses the same physical neurons to hold the shared meaning, but it sets up different readout axes, basically different viewing angles for English and Spanish. The neural axes literally rotate, which gives us perfectly distinct linguistic outputs without ever having to change that underlying constellation of meaning. By shifting the angle of how the rest of the brain reads those hippocampal neurons, it seamlessly pulls the Spanish word without triggering the English word, even though they live in the exact same geometric spot. I mean, it is an unbelievably efficient way to store massive amounts of overlapping data. Which brings us to Section 4, Human Brains versus AI. Fascinatingly enough, this complex biological mechanism shares some striking similarities with how cutting-edge artificial intelligence processes language today. Advanced AI models, like multilingual BERT, layer information in steps, essentially building towards a shared geometric understanding of concepts across languages. When you feed an AI a word, it doesn't instantly know its deep philosophical meaning. In the early computational layers, it's really just looking at the surface-level stuff, spelling, grammar, word order. But as that data moves down into the deeper layers of the neural network, the AI strips away the language-specific grammar and extracts pure meaning, plotting those concepts into a geometric space using distances, exactly like the human brain does. And at layer 11 of this AI model, we actually see a peak in cross-language similarity that perfectly mirrors the neural maps found in our own hippocampus. In the AI's early layers, there's no match at all. But right here at this deep semantic layer, the AI and the human brain seem to arrive at the exact same mathematical solution for organizing meaning. But there is a catch. While AI maps words into a shared space and aligns them almost perfectly on top of each other, the human brain adds a unique biological safeguard. Think about it. If our words were perfectly aligned on identical pathways, they'd be constantly interfering with each other. So we implement that brilliant geometric rotation we talked about. Same neurons, different readout axes. It allows for both a shared universal understanding and totally separate linguistic control. So I want to leave you with this provocative thought about your own mind's incredible built-in architecture. Your hippocampus already has the distances between dog, wolf, and fork mapped out in a universal geometry. You don't actually have to build a new map from scratch when you decide to learn a new language. You literally just have to learn how to rotate your neural axes to see that map from a new angle. The foundation for every single language on Earth might already be beautifully structured right there inside your head, just waiting for you to unlock the right geometry. Keep learning, and I'll catch you on the next explainer.